Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we're going to continue what we started in the last video. In the last video we wrote code to solve the towers of Hanoi using a recursive algorithm. In this video we are going to animate this in a way that will hopefully make it easier for you to visualize what's going on. So in order for this to be graphically demonstrated, we need to have the basic setup for doing our graphics. So let's go ahead and let's import the Scala Swing libraries. Let's import java.awt.color, and I'm probably also going to want java.awt.geom._. We will create a panel in which we will override the paint method. And this is where we're actually going to draw out our stacks of pegs. And then at the bottom, of course, we'll make a frame. And we'll open up that frame. Okay. Things we need to do in here. One thing I'd like to do. Oh, and yes, preferred size equals new dimension. How about we go with a 600 width and a 300 height. Let's come down here and let's remember to center on screen, because it's particularly useful for when you watch the videos to have the window actually pop up on the screen. Let's not go to 30. That would be a very bad idea here. Let's do 5. Run this, make sure that, whoop, that needs a new. Make sure I haven't put in too many typos and that a window actually pops up. Okay, so there we go. So what does the panel need to do? Well, I want to blank out the background. And I guess I'm actually going to pick to do a black background for this. And size.width. Size.height. After blanking out the entire background, I need to draw the disks on the different pegs. So let's run through the different pegs. And I actually want to run through their indices, not just the lists. And the reason I want to run through the indices is because I need that index to specify the X location for where I'm going to draw these. So we made this so it's 600 by 300, which basically means that each peg gets 200 pixels across for itself. And then what I want to do is I want to draw the different disks that are located on the peg. So let's have another for loop. And once again, let's do val len equals peg sub p dot length, because I'm going to need that. Go through the indices there. I want it so that the bottommost disk which will be at length -1, touches the bottom of the window here. We could set how thick we make our discs. At least for a first cut, I'm going to make them, I don't know, 50 pixels, 20 pixels, 30 pixels. How about I go with 30? Okay, so I want to draw a rectangle, and let's remember to set our paint color to something different. I'll just draw red discs for now. And okay, width val disk width equals peg sub p sub d. So the d, this is running through the indices there, so this is the number 1 through 5 as it's set up right here, 1 through however many we make these. That just comes off as an integer. So I think I'm going to make it so that each of these gets about 20 pixels broader at each step, and we start at 20. So if there were a size 0, it would be 20 across. We're starting at size 1, so it'll wind up being 40 across, and the next one up will be 60 across, and the next one up will be 80 across. And so then my X location here is 100 plus P times 200, because my pegs are separated by 200 pixels each, and I want them centered on on the middle of that. And then I need to subtract off disk width over 2. The height that I'm going to draw these at is going to be, let's see, 300 minus, and then I need this next value to be relative to how much d is less than len. So how about we go with 20 times len minus d. The width is disk width. Let's go ahead and let's enter, and the height I am going with 20. Right now I have quite a few magic numbers in here, and so there are actually 20s being used for a number of different purposes. This is not ideal. It's something that we'd want to change, define some constants for how big these things are. But for right now, I'm just doing this quickly for the sake of this video, so I'm going to leave it in this format. And what I want to do in here is, after each move, I want to repaint my panel. And then so that we can watch this, I'm going to sleep the thread. Let's go for 1/5 of a second, so we should get about 5 updates per second. And there we go. So, yay, we saw the towers of Hanoi. I think this might be a little bit easier to see if I make the discs one thinner, so there's actually a pixel width in there. This doesn't necessarily illustrate the algorithm all that well. It probably could if I were to try to slow it down a little bit. But it might be interesting to try to put in some color coding for what move we're doing right now, so that when we come into move stack, we record how many elements we're moving from and to, so that we can so that we can specify how many disks to highlight on each one of these. And so to do that, what we could do up here is define some vars. The highlight peg, I'm going to start off at 0. It turns out we're going to reset it every time before we So I'm going to highlight the things that are on peg, on the peg that we're moving from, and I want to keep track of how many to highlight. Which will also start off as 0. Okay. And what I want to do here is inside of this, before I do my drawing, I'm actually going to change the color. So if P is equal to highlight peg and D is less than highlight count, then I'm going to do G dot set paint color dot blue else G dot set paint color dot red. And since I've gone ahead and spaced this out, let's go ahead and let's put our curly braces in here. Remember, the advantage of doing this is Scala does not care one bit about the indentation, so if we were to add a second line to either one of these, if we don't actually put the curly braces, that can lead to some hard to detect errors. Let's see if that is... So what's being highlighted at each step there is something that shows you how much is moving. This is probably still running a little bit too fast. Let's go to just 2 frames per second. I also know why this is 2DD, paste. So we're going to repaint on every call, some of which aren't moving things. There we go. That makes it more obvious what's happening. So the recursion winds up starting off, so when we say we're going to move 4, well, that says it's going to move 3, and that says it's going to move 2, and that says it's going to move 1, and then the 1 moves. Nope, and I don't have a repaint at the end, so I didn't actually draw. Go ahead and put the repaint back in there. So you can see the calls that say they're going to move something, wind up cascading down, and then when it gets to the top, it actually moves that thing over. There are probably better ways to come up with color coding this to help illustrate it, but hopefully that gives you some idea of what's going on here. And of course, if we wanted to illustrate this for larger stacks, the program is perfectly general, and it can do so. Of course, with 8 disks in here, this is going to take a little while longer because we're only doing 2 moves per second. However, you can hopefully tell that as a human, you really don't want to do this by hand for all that many elements, because it does grow exponentially. So that's it for this video, and we'll see you again next time when we look at yet another example of recursion.